Okay, let's start class. So last time we talked about model assessment, and we have three approach for the model assessment. One is the internal approach. So here you can see there are three types. One is the in-sample error approach. So we can have without adjustment. That's no good. Why? Because we have in-sample optimism. Because we use the same data set to train the model as well as to evaluate. There's kind of bias, and that bias is called in-sample optimism. But with adjustment, that can remove such bias and can help us to identify the good models. So those with adjustment are related to all kind of information criteria that we talk about, AIC, BIC, and also mellow CPs. So this is the in-sample approach. However, there's a potential problem for this in-sample approach. Why? Because the in-sample approach tends to find a model that minimizes the in-sample error. Okay, remember what is in-sample error? In-sample error is the model performance on the sample points that has the same X on the training model. So Y can change, the response variable can change, but the X variables are fixed as the same, so same as the training. Okay, so in general, we want to use this model, fitted model, to predict those sample points that may have different X values. So that's called the generalization, extra sample performance. So how to find a way to choose the good model that can minimize the extra sample errors. Okay, so that leads to the internal approach and the external approach. So let's start here. So the internal approach is the validation set approach. That's a commonly used. So suppose we have a data set. Okay, we want to find a model that can minimize the extra sample error. So what we can do is we can split the data set into training and validations. Okay, so we fit a model on this training and then estimate its performance on the validation. Okay, so let's see an example. This example, we've already seen that previously. So we want to find the model that use the horsepower to predict the mile per gallon MPG. Okay, so we have about 400 observations, half as training, half as validation. Okay, this is not a good split, but just as an illustration. So we find both. So here, so the good things for the validation approach is very simple, straightforward, and easy to implement. Okay, but let's see the results. So here, we want to find out what is the optimal order for the polynomial regressions on these models, on these data sets. So we have the degree of polynomial as the horizontal axis, the vertical axis is the mean squared error on the validation set. So we fit the model on the training set, half-half, 50 as training, 50 as validation. Fit the model on the training, then evaluates performance on the validation. So that's the results. But the question is, there are many possible splits of the data. Is that right? Why we just use that split? So this is just one possible splits of the data. So we got this. You can see on the right hand side, you can see we have multiple splits. Each split, we fit the polynomial models with order is 1 through 10. And you can see their validation set performance. So you can see there is a big variation, right? So if we use this approach, so what is the optimal model? That minimizes it. Maybe not so sure, but maybe this one, right? But it seems to me quadratic is good enough because it's close to the best, right? However, if we use this, you can see we can have a different results. Like let's see the one that at the bottom. So what is the best one? It seems to be the order at 7 is the best, right? And you see this one, it seems to me order at 7 looks like the best. But some of them, like for these purple ones, it seems to me the quadratic model is the best, right? So you can see there are lots of variations. So which one we should use? Yeah. So that can help us to see what is the drawback, right? So the drawback is the validation MSE can be highly variable. Only a subset of observations that are used to fit the model, and the static model tends to perform worse when they trained on fewer observations. So that's another important point. So if we just have 400 data points, we do an even split. So the model that we fit on training only 50% of the total data. That could be substantially worse than using the full model, using all the data sets, right? So that actually introduce some bias. So the model will be too simplified, especially we have a small sample size here, right? So how do we relieve this problem? So there is a way to relieve this problem through, there's a technique called cross-validation, okay? And the cross-validation has a special case called leave one out cross-validation. So what it means is, let's say if we have a data set, we have n observations. So each time we just left one observation out. So the orange one is the one that we left out. And use the blue one, the rest of the data points, to fit the model. And then predict the sample that we left out. Right? But that's just one result. Okay? And we do that repeatedly. So every observation has been left out once. You see that? Left out once and only once. So now in this case, in this way, so we have a cross-validation every time we left just one observation out, and we find out its MSEs, so we add them together. So that will be the mean squared error for the cross-validation error. And why this is better? Because this time, if we have a small sample size, so how many observations have we used to fit the model? We used as many as we can. How many? If we have a 400 observations, so we use 399 observations. So that model will be no big difference from using the full data, right? So we can reduce that bias. And also for the validation error, each observation has been left out once and only once. Okay, and also this approach is not random, not it's not a random number. It's a fixed deterministic number. Why? Because there's only one possible case. You leave one observation at a time. So there's no randomness for the MSE based on the leave one out cross-validation. So that's why this is also a very good for a good choice for the validation, and especially useful for the small sample size. Okay, but a problem comes is if the M is quite large, let's say a few thousand, then that's also time consuming because we have to fit the model how many times? N times. If M is 1,000, then we have to fit the model 1,000 times. For small sample size, that's fine. For relative large, that will be problematic. Okay. However, there is a shortcut for the leave one out cross validation. Okay. So for some model, okay. So what do I mean for some model? If the model is a linear fitting model, okay, be careful. Linear fitting model is not linear model. It's not just linear model. Okay, linear fitting model is the model that we can show the y hat. The fitting model can be represented as a projection matrix S times 1. And I will show you some examples. So we can have some nonlinear model which belongs to linear fitting method. Okay, so if the model is a linear fitting model, it includes the linear model, but it's more than that. Then we can show that the leave-one-out cross-validation can be calculated just once. We don't need to fit the model multiple times, just once, using all the observations. Okay, and then the formula to find out the leave-one-out cross-validation error is this one. Okay, so this is the estimated value for the i's observation. And this is the yi, that's the i's observations response value. Okay, and divided by 1 minus SII. So what is SII? S is that matrix. That's called projection matrix. This is a squared matrix. And what is the dimension? It's n by n. Okay, so if it's a squared matrix, okay, n by n, then we have a diagonal. So the diagonal elements is notated as SII. Okay, so what is SII? Like the first row, first column is called S11. Second row, second column is S22 up to SNN. Okay, so these are the diagonal elements, and these are the SIIs. So we can mathematically prove the leave one out cross-validation error is equivalent to this. So in that way, we just fit model once. So that's a shortcut. Okay. So leave one out cross-validation, and there is another cross-validation called a k-fold cross-validation. It's not just leaving one observation. It's split the data set into k-fold. Okay, for example, if we have a data set like that, and then let's say we set the k to be 5. Okay, so that means we have 5-fold cross-validation. So what we did is we have a data set, we have a split, usually equal split. Okay, but if you cannot have the exactly equal split, that's fine. Just try to be each folder contains about the same size. Okay, then we use the blue ones as the training set to fit the models, and then evaluate the validation performance on the orange set that we left out. And do that once and only once. So each fold has been left out once and only once. So k-fold means what? K-fold cross-validation means we have to fit the model 5 times. Each time we left one fold out. Use the rest of the folds as a training set, fit the model, predict the one that we left out. Okay, so you can see the connection between the k-fold and the leave one out. Did you see that? Leave one out cross-validation and the k-fold are the same when what? When k is equals to what? K equals to n. When the k is equals to n, n is the sample size. then k-fold is the same as leave one out, right? Okay, so you may ask, what's the difference? The difference is now this one is not deterministic, it's random too. Okay, but the good thing is that if the model is not like a linear fitting model, then we have to fit model each time. So k-fold, like a five-fold, we only need to fit the model 5 times or k times. So the computation burden is not too much. Okay, so this is especially useful for the large sample size. Okay, and use those computationally intensive algorithms. And we will see that like artificial neural network and like the ensemble methods. These are very computationally intensive algorithms. So using the k-fold is better than leave one out. So let's see revisit the car example. So the left one shows the leave one out and the right one shows the tenfold. Okay, so you can see the leave one out, that's just one line. It's deterministic. And for tenfold, compared to this one, right? That's the validation approach. Compare this one with this, you can see what is the benefit of doing the k-fold. It's much stabler, right? Compared to the previous one. Okay, and it has about the same trend as the leave one out. And this, if the model is not linear fitting model, and this is computationally efficient compared to the leave one out. Okay, so this is the simulation, the 3 simulation examples, and I use and I show the leave one out cross validation and tenfold cross validation on these 3 examples. Okay, so the blue ones, you can see the blue ones, these are the true test error. Okay, the black ones, the black dashed line is the leave one out, and the orange one is the tenfold. So you can see the leave one out, tenfold, they are very close, and these cross plays are the optimal models that will be chosen. So you can see leave one out and cross validation, they have very similar results as the true ones, right? So they are quite close. And like this one, right? Similarly, so you can see the effectiveness of using the leave one out or tenfold cross validation, k-fold cross validation to to find out the best model. And by the way, this blue line is not based on the training set, test set, it's based on the truth. Okay, so you can see in practice, instead of using the AIC, BICs, which find the model optimized on the in-sample error, we can try the cross-validation approach. Okay, and should we use leave one out or k-fold? It depends on the sample size and depends on the type of models. If the model is linear fitting and a small sample size, I would say go with the leave one out. If the sample size is quite large and the model is not linear fitting, then go with k-fold. Okay, and otherwise there's not too much big difference between these two. Okay, so you can choose either one. Okay, so leave one out and cross validations is also related to the bias variance trade-off. So that's why I said this bias variance trade-off is a fundamental principle in the statistical models and machine learning. Okay, so what is the bias? So the bias is if we do the cross validation or the validations, the sample size will be smaller than the full data set because we just use a subset to train the model and evaluate the model performance on those observations that left out, right? So in that way, you can see which approach has the least bias. The least bias approach is the leave one out because we only leave one observation out. So that's why the leave-one out is less biased, but leave-one out has high variance than the k-fold. Okay, that part you will have questions, right? Because you can, I just said in the previous slides that leave-one out is deterministic. There's only one way to do the leave-one out. Why I have leave-one out has the higher variance, right? That's the question. So, but what I'm talking about is really two different things. Okay, so first is leave-one out cross-validation is deterministic approach. There's no randomness. That is only true if we have a data set given. For that data set, yes, you are right. Leave-one out is deterministic, is fixed. You just give me that number, that's it. There's no other possible value for the leave-one out for this data set. That's true. But what I'm talking about here is has high variance is not within that data set, but between the data set. What does that mean? That means if we sampled another 400 data from the population and do the leave-one out, that can be very different. And that variance is high. Why? It's very intuitive. It very makes sense. Why? Because think about if you do the leave-one out, all these for this model performance using almost all the data for this model that I trained this model, the model performance is only evaluated on what? On a single observation. Tell me, is that very risky or not? Of course. So that's why I say the leave-one out has a very high variance. That is the variance that between the samples. You sampled again, do the leave-one out, you will find it's very different. But leave-one out is deterministic within that data set. That's true. So there are two types of variance. One is the variance within the data. One is variance between the data. So make sure you understand that. Okay. So I'm talking about the between. Okay. So that's why leave-one out has high variance than the k-fold. Why k-fold has less variance? Because that makes sense. You can easily see the model performance is not evaluated on one observation, but on a multiple observation, which is one-fold, which let's say if it's tenfold, 1/10, 10% of the data set are used to evaluate this model. That is more credible. That is more accurate than just estimating that model using one single observation. And I think that's totally makes sense, right? So that's the bias variance trade-off that I'm talking about. Okay, so which one is better in reality? I'm already said that if it's a small sample size, leave-one out has less bias, so that go with that. If it's large sample, k-fold is the best. Okay, so then you may ask another question. So when you say k-fold, how large is the k that works the best in practice, right? People have already thought about that and run many trials on different data sets, simulation, whatever, and people find that when the k is between 5 to 10, so fivefold, sixfold, sevenfold, eightfold, ninefold, tenfold, these are the great numbers. These are the magic numbers. Okay, so when you do the k-fold cross validation, use these numbers. Okay, and they usually works very well. And these are based on the empirical results. And you may ask, is there any proof? No, but empirically, this works the best. Okay, so that's the bias variance trade-off. And this one, so let me show you some cross-validation on the classification problems. Okay, the procedure is the same as the regressions, and you can see here I'm using the cross-validation to choose the order of the polynomials for this two-class classification problem. Okay, so the underlying purple dash line, that's the true boundary. Okay, because that's a simulation. Okay, so we know the truth. So this is the quadratic boundary with degrees 2. Okay, so this is 3 and 4 and so on. So this shows the error rate. The error rate is based on the tenfold cross validations. Okay, so the black curve is the tenfold, and the brown curve is the uh, uh, test error on a test set. Okay, and the blue curve is the training error. Okay, so you can see here for the based on the tenfold cross validation, the optimal polynomial is at the 4, but for the test error, it is minimized at 3, so very close, right? And this is based on the not the polynomial boundary, but the k nearest neighbor. Okay, so the horizontal axis shows the 1 over k. So you can see the based on the tenfold, this one minimize the cross validation error. Okay, but based on the test set, this one, so very close. So that also shows you the effectiveness for using the cross validations on the classification examples. So it works for both regression and classifications. Okay, and this is a simulation we have seen last time. So let's just revisit that. And I run the true function is that red curve. So it's a combination of the linear function and sine function. Okay, and I use the polynomial regression and I use the cross validation to choose the optimal order for the polynomial regression. And in the background, so I did tenfold and multiple times, and you can see in the background, these are each time I have gray lines that from the order is 1 through 10. So I do that repeatedly 50 times. So I do 50 replications. Okay, and the blue ones is based on the true errors, and the red ones is the average for these cross-validation errors. So you can see the cross-validation error is almost the same as the true errors. Because this is a simulation, we know the truth. We know the true error rate, right? So the true error rate is in the blue ones, but the red ones is based on the average of the tenfold cross-validation. So you can see they matched very well. Okay, and you may ask which one, so what is the optimal order? So if we focused on the prediction performance, okay, so if this study, we are mainly focused on the prediction accuracy. So I would say the optimal order is 9 because that minimizes the cross-validation error. But if the purpose is not prediction, but interpretations, so we want the model to have a simple model, which usually give us easy interpretations, right? So I would say just use the order is 6 because when the order is less than 6, the performance is much worse. But the order when reached 6, we have a good results. But when order increased, you can see it bounced up and then bounced below. But the difference between the 6 and the 9 is not that big. So I would say for the interpretation purpose, I would choose 6. Okay, so this is the cross-validation for the classification, and this is the code. So here you can see this is the formula that I used in here in slide 14. Okay, because for the polynomial regression, it belongs to a linear fitting method. So we can check the leave or not cross-validation through that. Okay, so, and for this one, that's the k-fold. So I wrote a function in the R for the k-fold. So you can take a look. So I don't have time to go over these codings. So if you want to learn R, it's a good example. So you can just read this sample code or just play with this code in the R. Okay. This is the Boston housing. Sorry. We've already see this example before. So I split the data into 100 observation as training, 406 as test. This is not a good split, okay? This is just used as an illustration. So for the multiple linear regression on the training set, and then we apply the tenfold cross-validation on the training set to estimate its performance. Okay, so here I used for the cross-validations, I used a function in a package called the boot package. That is for the bootstrapping, which we will talk about later. Okay, so there's a function called cv.glm. We will talk about generalized linear model in a minute. Okay, so cv.glm, it's a function that can do the cross-validation. So you don't need to write the code to do the cross-validation. It will do it. Okay, and k is 10. That means this is tenfold cross-validation, and it gives two numbers. Okay, so the first number, that is the tenfold cross-validation error without any adjustment. That's just the raw cross-validation estimate. However, remember I said that the k-fold also has some bias, right? K-fold has some bias. Why? Because the sample size is decreasing. Here, if we do the k-fold, we only use that many observation as training, right? That is, the model will be inferior compared with using the whole data set. And that is the bias come from, right? So how to adjust that bias? There is a way to adjust that bias, okay? So I won't talk about the details, but this function actually calculated the bias for you and then remove that bias. So the second number is the bias adjusted cross-validation estimate. So which one we should use? Either one is fine, but the better one is the second one. So the second one is adjusted the cross-validation bias. Okay, so this is the Boston housing, and the last example is the is this study from a clinical trial. So we have 164 subjects took part in this experiment, and the drug is the cholestyramine lower that which supposed to lower the blood cholesterol levels. So the subject was supposed to take 6 packets of these medications per day, but many of them actually took much less. Why? Because these medication doesn't taste good for the kids, so kids don't like that, and also the size is quite large, so it's not easy to swallow. Okay, so that's why after the study, they found that the compliance rate is actually quite low. Okay, so in these ways, so they want to find out the improvement and compliance relationship. And of course, that relationship may not be linear, right? So you can see it's like that. So the fitted curve is a nonlinear smooth fitting for the relationship between the compliance and the improvement. Okay, so here, what is that smoother? We will talk about more about these nonlinear smoothings in a minute, maybe next time. But anyway, this smoother is that I used is called the lowest smoother, which is one of the most popular nonlinear smoother. So this is based on the fitting the regressions locally. So we do the weighted, locally fitted linear regressions. Okay, so what does that mean? That means, let's say, suppose we want to estimate the improvement at, let's say, the compliance is 50. Okay, so when the compliance is 50. So first, Loess smoother has a parameter that you need to choose. Okay, we can call it alpha. So that's the neighborhood size. So we have 164. That's the total sample size. Okay, let's say, suppose the alpha, the neighborhood size is equal to, let's say, 25%. Okay, 0.25. So that means it's a quarter. Okay, so that means for this whole sample size, we should choose what? 41, I'm sorry, 41 observations, right, as our neighbors. That's about 25%. That's 41. Is that right? So how we select these, we just find out the 41 subjects that has the closest compliance rate that to the 50. Okay, so probably from here to here, let's say. So these are the observations that has the closest compliance value to the 50. And that contains about 41 subjects. Okay, so then we also have the weightings. So how does that mean? That means for those observations that closest to 50, of course, they will have higher weights because these observations are very close to 50, right? They should have more weights, okay? But for these observations which is close to the boundaries, which far from 50, like these points, they should have low weight compared to these points. Does that make sense? Right? So how do we weight? There's a formula there. Okay, you don't need to worry. So there's a formula there. It assigns the weights. So then we fit a linear regression line. Okay, so let's say we fitted a line, and this is the fitted line. Okay, so for after that we fitted a line using the weights and these samples in the neighborhood, and the line that hits the 50, and this is exactly the points that we fitted at 50. Is that clear? So that's 50. So you may ask, what about 51? Same thing. So if you are talking about 51, then what we do is we move to the 51, right? And we find out the neighborhood size that contains 25%. And then we do the weightings and fit the linear models. Let's say here, then the one that here is the fitted. And just do that on a fine grid. Then we connect these points. Okay, so that is called the Loess smoother. And this is the fitted smoothed curve. It seems like complicated, but you don't need to do it by hand. The software will do that. Okay, so the neighborhood size is called alpha. So here I'm showing in this fitted curve, I used alpha is 30%. So each neighborhood size contains about 30%, about one third. And the weighted least square is that, and the weights is here. And this is the weights. Okay, so in the R, that Loess smoother can be implemented using this function. So the Loess is the function in the R to fit the Loess smoother. And the alpha, the neighborhood size, can be specified in this function. There's an option called span. So span is the option. So you can see here, this is sample code. When I do the, let's see, where is it? Loess, you see that? That function, we have the span equals to what? Okay, so the span is the alpha, that to specify the alpha, neighborhood size. Okay, so here I used another function in the R called cross-val. Cross-val is a function in the Bootstrap library. This is a generic function to calculate k-fold. So you may ask, why we need to have another one? Why? The reason is because the one that we use here, cv.gl, is only for the generalized linear model. Okay, you may ask, what is generalized linear model? We will talk about that in about 10 minutes, and you will see that. Okay, and right after this, we will talk about generalized linear models. So that is only a group of models called a generalized linear model. So if the model is not generalized linear model, let's say artificial neural network, right? It's not generalized linear model at all. So that cannot be used for 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 the model which is not generalized linear model. Okay, so this is more general. The C cross val that can be applied to more general functions. Okay, so that's the purpose, and you can see the sample code to run that. So here I use tenfold cross validation 20 times. So I run once. Why? So what does that mean? Tenfold 20 times. So for a data set, we have 161 or 64 observations, right? So we can have one tenfold split. Okay, so then we do tenfold cross validation for this split once. And then we can have another split, still tenfold. Is that right? Because there are many, many, many ways to do the tenfold split. And that in that way, we can do the tenfold cross validation again. And we repeat that process 20 times. And you may ask why we need to do that. There's a reason behind that. Why? Because as I showed you here, the tenfold cross validation is actually still not fixed, still have some variations, right? So sometimes we may not be able to choose the best one. So the best approach is just take the average so run the k-fold cross validation multiple times and then do the average. And that usually gives us the best results. And you can easily see that from here also. You see that each gray curve is a tenfold cross validation. You can see there are some variations. But when we do the average, that is shown in the red curve. You can see the red curve is very close to the truth. So that is the reason. Okay, so it's not just showing you that there's a reason behind that. Okay. Okay, so look at the code. So I don't have time to go over this code line by line. So if you have any questions, we can talk about that after class. And this is the blue one is the average of these 20 replications for the tenfold. Okay, so you can see quite noisy for this tenfold. So, but when we do the average, it's much stabler. Is that right? And what is the best? The one that minimized the average, which I would say the population or the neighborhood size is 50. So the alpha should be, the optimal alpha should be 0.5. So that's how we choose the optimal alpha through the cross validation. Is that clear? Let's see. Yeah, that's the end. Any questions for the model assessment? Okay, if you don't have any questions, let's move to the uh, generalized linear models. I've already posted that in the Moodles. So if you haven't seen that, so for this one, I just created an HTML file, so not PDF. So I think this is a better way to show the generalized linear models. So why we need to have the generalized linear model? Okay, because we have some limitations on the linear model, linear regression models. So what are the limitations? I know that linear model, linear regression model works very well for some data sets, very useful, very commonly used, but it most of the time it only works well for the response variable follows a normally distributed distribution. So if the response is not normally distributed, let's say it's possible that the response is binary, just has two possible values, 0 or 1. So obviously we cannot use linear regression anymore because it's not normal, right? Or maybe the y is counts, like the counting 0, 1, 2, 3, these are the integers from 0 to infinite, right? So that obviously also cannot be used. We cannot apply the normal for the linear regressions. And the y is positive, continuous, but it's highly skewed, like the gamma distributions. So in this case, still we cannot apply the linear regression model because it's not normal. It's highly skewed. Okay, so that's one reason. And another reason is that for the linear regression model, we have an assumption that's the homogeneous of variance. That means the variance for the response is constant. So what if they are not, right? So we cannot use. Okay, so you can see that linear regression model is limited. Only allows certain response that can be used as the in the linear regression model. Okay, so that's why we need to have the generalized linear model. Okay, so it's more general. So generalized linear model includes the linear regression models that we know as a special case, but it's more than that. It's a family. Okay, it's a family of models. So that's why it's called generalized linear model. So it has three components. Okay, so we can see these three components through this illustration graph. So here, for the x1 through xp, these are what? These are the input variables, the x variables. Okay, then we have the first component, that's the systematic component. You can see for the systematic component, that looks exactly the same as a linear model. It's a linear model, has the intercept, has the slope, has the x, and so on, right? So that's why it has a linear model term here, okay? And then the second component is the link function. So what is a link function? Link function actually links the expected value of y to the linear model part. So that's why it's called a link function. It connects the expected, the E means expected value of y with the linear model part. So what is the connection? The connection is through that function called g. Okay, we will show you some link functions in a minute. Okay, so that's why it's called generalized, because for the linear regression model, it is what? It is the expected value of y equals to this. And that's the linear regression model that we talked about before. Okay, so in the special case, you can see when the g, that link function, is an identity function. It's just by the argument itself. If the link function is an identity function, then the GLM becomes what? Becomes the traditional linear regression model. You see that? That's the connection, okay? But it can go beyond that, right? So that's why it's generalized linear model. Okay, and the third part is the output part, which the y follows a distribution. Okay, so that's the random component part. So it has three parts: systematic component, link functions, and the random component. Okay, so let's see some details. For the random component part, this specifies the probability distribution of the response variables. So that means the y follows some distributions. Okay, so this notation means the y, which is a response, follow some distributions. So what kind of distribution we can handle in the GLM? So there are many, okay? So I'm just listing some examples, like the normal distributions, binomial distributions, Poisson distributions, and so on. Okay, so that's just some three examples. So then you may ask, does that include all the distributions that we know? No, that only includes a subset. Okay, and then you may ask, what are the subset that was included? Right? And these subset, these distributions need to satisfy a certain condition. Okay, what condition? That condition is called the distribution has to belong to a family. And that family has a name called the exponential family. Okay, this seems to be very technical. Like that family has to be written, can be represented in these ways in the PDF form, the probability density function. But you don't need to know. I'm writing here just if you are interested, you can look some details. Okay, but you don't need to know that. Okay, but here in this formula, you can it actually shows there were three specific functions A and B and C. Okay, so these has its own meanings. Okay, so here I'm just showing you. So there is also two parameters. One is the C and one is the psi. Okay, theta is called canonical parameters that represents the location for that distribution. And the psi is the dispersion parameters that represent the scale. So just think about a normal distribution. Okay, I, I, I think you should know the normal distribution, right? For the normal distribution, we have two parameters. Is that right? We have a mu, that's the mean, and the variance, that's the sigma square. Is that right? So just like that, okay, you can consider the theta as the mu, which is the location family, okay? And the psi is the sigma square, that's the dispersion parameter. And that's actually true for the, if the y follows a normal distribution, it is true. Okay, but it's more general than that. Okay, so that just gives you some idea what is the theta, what is the phi here. Okay, so if we have this distribution family called exponential family, then we can mathematically prove that the mean for the response is equals to this one. Okay, so what is the B theta? You don't need to know the proof, you don't need to know these details, but this is the first order derivative for the B, okay? And this is the second order derivative for the B times the A, okay? So it's a little bit complicated, but you just know that as long as we have this family, okay, we can easily find out the mean and the variance because the formula is there. Okay, so that's the random component part. So y has to follow some distributions, and that distribution must be belongs to an exponential family. Okay, okay. The second component is the systematic component, which is a linear function. Okay, so that part you already know that, and it also can include the interaction terms. Okay, like in the linear regression model. And the third one is the link function. And that link function specifies the link between the random components and the systematic component. And this indicates how the expected value for the response relates to the linear combination of the explanatory variables. Okay, for example, for the classic regressions, the link function is actually the identity function. Okay, and for the logistic regression, which we will see in a minute, the link function is what? The link function is the logit function. Okay, and we will see that in a minute. Okay, so any questions so far? Okay, so before we talk about examples, I also need to talk about assumptions, right? Just like linear regression model, we have assumptions. For the generalized linear model, we also have some assumptions. First one, independent assumption. Okay, and second one, the dependent variable doesn't have to be normally distributed, but it should follow a distribution that comes from exponential family. Normal distribution is a member in that family, but the family includes more than that, such as it can include the binomial, Poisson multinomials, and so on. Okay, so a GOM does not assume a linear relationship between the response and explanatory variable, but it assumes what? It assumes the G mu equals to a linear function, and the G is the link function. Okay, so it does not assume a direct linear relationship between the y and the x, but through the link function, there is such linearity. Okay, so that's the, and the homogeneous variance assumption does not need to be satisfied. In fact, it's not even possible in many cases. Okay, so no constant variance assumption anymore. An error needs not to be independent, but not normally distributed. Or, I'm sorry, needs to be independent, but not normally distributed. Okay, and for the parameter estimates, instead of using the least square, we use the maximum likelihood estimation. So this is the estimation approach. Not OLS, not through the least square, but through the maximum likelihood. Okay, yeah, why exponential family? You may have this question, and I don't want to touch the details, but the exponential family is to unify numerous models within that family, that so that we can have the same optimization in the softwares. So by using these exponential families, the way that we estimate the parameters through the MLE, maximum likelihood estimate, will be the same algorithm if the distribution is coming from this same family. So it's like a family that we can use the same way to estimate and to interpret the models. So that's mainly for the convenience purpose. Okay, so now let's see the examples. So first example is the simple linear regression. That example is, you should very familiar with that. So this assumes the expected value of y, which is called mu I, is a linear function of x, right? So the y can be write as, so we have, this is one way to show the linear regression model. Another way to show that is just the yi equals to what? Equals to the beta 0 plus beta 1 xi plus epsilon, right? They are the same. They are exactly the same. If you can easily, if you just check that, they are exactly the same. So it's just to replace the mu I by what? By this part. Then you have this, right? So why I need to write in this way? Because that way you can easily see what is the link function for the simple linear regression. The link function is just the identity function, because the mu I is just the expected value of yi, right? So that is mu I, okay? That's the notation, okay? So the link function is just itself. And this also applies to the multiple linear regressions, okay? So The link function for the linear models, simple linear model, multiple linear model, it doesn't matter. It has the identity link. Okay, so the G E Y equals to the EY itself. That's the simplest link function. Okay, now let's see more complicated case. Now this time we're talking about the response which is binary. Only two possible outcomes, 0 or 1. That corresponds to success or failures like that. So what is the link function? Link function is this one. Okay, so you may ask, what is this pi? Pi is the expected value for the y. Okay, yi is 0, 1, 4. Okay, just like a toss a coin, head or tail, right? What is the expected value for the yi? That is the probability for that to be the 0 or 1. Does that make sense? So that's the expected value. Okay, so the pi is the expected value of y. Okay, so what is the link function? Link function is called logit link. Logit link is the G E Y is equals to what? Is equals to the log. I'm replacing the pi by the EY so that you can easier to understand. Expected value of y, 1 minus the expected value. So of course, this is a function of expected value of y, right? And that function, there's a name in statistics called the logit. Okay, so the logit link is the link function that we use for the logistic regression. And that's why it's called logistic regression. Okay? What is that? Yeah, this is, I can talk about that after class. Okay, so that's the link function, is the logit link that connects to the systematic. And also, what is the random component? The random component is the binomial distribution. Okay, so the binomial distribution, we can write the PMF, the probability mass function, in this way. So I hope you understand that. The first one is the binomial coefficient n choose y, okay, times the pi, that's the probability of being 1 to the power of k times 1 minus the probability of being 1. So what is 1 minus pi? That's the probability of being what? 0, right? So the pi is the probability of being 1, then the 1 minus pi is the probability of being the opposite outcome, which is 0, right? Okay, so to the power of n minus k. So that is the chance, that is the probability having k ones and n minus k zeros. Okay, so that's the binomial probability. For example, if I have a fair coin, okay, let's say for a fair coin, let's say the probability of being head is 0.5 and the probability of being tail is 0.5. Okay, so I flip the coin 10 times. What is the chance of getting 5 tails? So the first one will be what? We will have 10 trials, 10 flips, right? We'll have 5 tails or 5 heads, let's say, to the power of. So what is the chance of getting the heads? 0.5 to the power of, how many heads do we have? 5 heads, right? Times 1 minus 0.5. So that's the chance of getting the tails to the power of 10. We have 10 flips minus the 5 times that we got the heads. Okay, so that's just an example for the PMF in the binomial. So this is the random component. Okay, so the link function is the logit function. Okay, so that's the second example. And the third example is the Poisson. So logistic regression has the response is binary. But Poisson has the response is what? Not binary, not continuous, but what? But a count. So it's a discrete but count response variable. So the count, so the possible values for the y are what? Are the 0 and 1s, 2s, those integers. And these are the possible values for Poisson regression response values. Okay, so in the Poisson regressions, we want to find out how the mean of a count depends on a set of explanatory variables. Okay, so this side is the systematic component, that's a linear function, and this is the link function, which is a log link. It's not logit, it's a log link. Okay, and what is lambda, you may ask? Lambda is the expected value of y. So that's the expected counts. Okay, and that is lambda. So the log of the expected, so the log of the expected value of y, and that is linked to the systematic component, which is a linear function of x. So the so the link function is log function, not logit, log. Okay, and this is the PMF for the Poisson distributions. Okay, so here the k is the observed count. Okay, and lambda is the expected value for the y. Okay, and the e is the exponential function, and that's the probability of observing k counts. Okay, so for example, let's say we observe the number of car accidents on a certain location on the highway, let's say I-10. Okay, so let's use the week as a unit. Okay, so for each week, the expected number of car accidents, let's say is 3 in this intersection highway. Okay, so the lambda will be equals to what? 3, right? And then if we know that, okay, then you may ask, so what is the chance of observing 5 car accidents this week? So if we assume this follows a Poisson distribution, then what we can do is we have the expected number of accidents, which is 3 to the power of what? So what is the chance of having 5, right? So it's 3 to the power of 5 times the exponential function to the power of -3. Okay, then divided by this k factorial is what? K here is 5, right? We want to find out 5 factorial. So that means 5 factorial means 5 times 4 times 3 times 2 times 1. So that is the factorial. Okay, so that is how we calculate the probability of observing 5 accidents in that location if the average expected car accident is about 3. Okay, so this is the Poisson regressions. The underlying random component is a Poisson distributions, and the link function is the log link. Okay, so these are the 3 examples. Any questions? Okay, so to summarize, the GLMs is, so why we need to use GOMs instead of the traditional OLS, ordinary least square fittings, because we do not need to transform the response to a normal distribution. And the choice of the link is separate from the choice of the random components, so that gives more flexibility in modeling. Okay, and the models are fitted with maximum likelihood estimation, which is more general. And also the MLE has some very nice uh, properties if the sample size get larger. And in statistics, there's a name called asymptotic performance, asymptotic property. So that means if the sample size grow to infinite. So what is the property for the solution? So that's called asymptotically. So we can prove that. The likelihood function and the parameter estimates actually follow some asymptotically normal, and also we can use the chi-square and normal distributions to do the statistical inference. Okay, so these are the benefits, and also all the inference tools and the model checkings that applies to the logistic also applies to the Poissons, to any models, as long as this model belongs to the generalized linear model families. Okay, so that's the another benefit. It's more general, and the inference is unified. Okay, and there's often one procedure in a software package to capture all the models. So if you use SAS, you can use proc gemmod. In SAS, in the R, you can use GOM functions. Okay, so here, let's see some examples. Okay, so this is a very classic example in the generalized linear models. That is the from the 1986 crash for the Space Shuttle Challenger. This was linked to the failure of a certain part in the spaceship called O-ring seals in the rocket engines. So data was collected on 23 previous shuttle missions, and the launch temperatures on the day of the crash was 31F, which is extremely low. Okay, so you can see from this study that there is a reason why the shuttle Challenger uh, has a crash, has the accident, because on that day the weather is too cold. So actually, when it's cold, the chance for that O-ring seal has a problem is much higher. Okay, so this is a real data set, but connect to a sad accident. So here, this data set is in this package called far away in R, and data set's name is called ORIMS, and I just listed the first few. Okay, so here you can see the response is uh, is really the binary. Okay, so this follows a binomial distribution. So the response is binomial. So this you can see here we have 23. Let's see. Oh, yeah. So here the temperature is temperature at the launch, but damage is the number of damages incident out of the 6 possible. So there are six rings. So you can see here at temperature is 53, it damages 5. 57, only 1. 58, only 1. 30, 63, 1. 66, 0. 67, 0. That's just the first 6 observations. So the number of damage follows a binomial distribution. And the range is what? From 0 to 6, right? So that's the number of O-rings that that has that was damaged, and there are 6 rings. Okay, so it cannot go beyond 6, it cannot go below 0. Okay, so 0 is the perfect case, no damage at all, and 6 is the worst case. Okay, so to do that, we can use the logistic regressions, right? So here, wait a minute. So I use the GOMs. If we have the data like that format, so we can have the damage and the Columbine damage and 6 minus damage. So this is the number of damages among these 6 rings, and this is the number of rings that not damaged. Okay, and which follows the systematic component part is temperature. Okay, so this is the response, and this is the explanatory variables. And the family, what is the distribution should we use, right? This family means which distribution you should pick from the exponential families. So here we use the binomial, and the link function is the logit. Okay, and that's how we do the analysis in these examples. And so we have this is the estimate of the intercept. This is the temperatures, coefficient for the temperature. So you can see here the number of so the when the temperature increases, the number of damages what decreases. Is that right? Because the coefficient is negative. So that means when the temperature when the temperature goes higher, increased, the number of damages is what goes below goes smaller. It's the opposite. That's why it has the negative coefficient, right? And on that day when launched the Challenger, so the temperature is very low, and that's the main reason that caused the accident. Okay. And here, this shows the temperatures, and this shows the probability for having the damage. And you can see here when the temperature is high, is over 65, you can see the chance of having damage is very low. But when the temperature is close to 50, you can see the chance is very high. And on that day when launched is 31, something like that. So it's the probability of having the damage is almost 1. Okay, so that's the okay. Let's see. So now let's and here I don't know if you have a question or not. I'm talking about for the logistic regression when I say that the response should follow a binary, right? It's either 0 or 1, right? But here, if you look closely, it's not 0, 1, right? It's the number of damage here. It's from 0, 1 up to 6. So why this is still called a logistic regression? Okay, so this actually is still 0, 1. Why? Because for each ring, it is 0, 1. Is that right? For each ring. But here we observed 6 rings as a batch together. So that's why we just record it as 5 for that batch, 1 for that. So that's one way to show it. And there's another way to show this data, exactly the same results, if the data set looks like the like the first one. Temperature is 53, we observed 5 damage, right? So what it should look like is we should have one of them is 53, 0, and then 53, 1, and the 53, 1 again, and up to 5 ones. And that's actually the first 6 data points. Okay, so this is the first row actually means these 6 rows here, which follows a 0, 1. Okay, but sometimes you can see it's more meaningful to just save the data in this ways so that we can have fewer number of rows. Is that clear? So this data looks like it's not binomial, it's not binary, but it is binary. Okay, so just keep that in mind. That's just one way to represent the data. You can also represent the data in this way, but if you use in this ways, you don't have to write in this. You can just use the damage directly. Okay, so if you save the format in this way, is 0 or 1, then if you put damage here, and damage is binary, then instead of having the column bind damage 6 minus damage, you can just use damage itself. So this is the tricky part. Okay, so I think let's see. I don't have time to finish the rest, so I will continue that. And but read the slides. And the next one is, so for the logistic regression, that's not only link. We can have some different link function for the binary response, like the probit model. Okay, so we will start that next time. Any questions before we start? Okay, so let's start here.